right, for the final piece for assessing model conditions, we're going to go over how you can assess the normality of the distribution of residuals, as well as assessing equal variance across the regression line. So each of these have two components. We'll first specifically talk about what the condition is and how we can use R to assess these conditions, and then I'll walk through an example in the context of a data set that we've been exploring for these videos. So we'll start with thinking about, we fit a multiple linear regression. So here is our multiple linear regression model. We notice that we fit this sort of interaction model that allows for us to have different intercepts and different slopes for our different sexes of professor. So we're modeling their course evaluation score based off of their average beauty score, and I'm allowing for that those lines to change based off of the sex of the professor. So this is my multiple linear regression model that I have, and I've stored this model inside of this variable or this object that I called beauty underscore score underscore LM. So I would suggest that you do this in your project and in your lab assignments, because this is allowing for you to use this linear model that you fit for other explorations. And I would highly suggest that you give your linear model a name that makes sense so that you don't have trouble recalling what you named it later on. So first, let's think about normally distributed residuals. So the idea is that the observations are varying symmetrically around the least squares regression line. So if you were to look at a specific point on the least squares regression line, say here, that the observations fall in approximately a bell-shaped curve around the regression line in this, specifically for professors who have an average beauty score of 6. So we're saying that that looks like a bell-shaped curve, which is a little bit difficult to visualize. So maybe it's a little bit easier to visualize the distribution of the residuals of our regression line and see if the residuals appear to resemble a normal curve close enough. So here we never say that our residuals are, we know that they're normal because we never actually know that they're normal. So what we can say that it appears that they're close enough to the normal curve that the condition is not violated. So I do want to point out that this condition is less important than the condition of linearity or independence, because the least squares method is an unbiased estimate of the population model. So we still obtain unbiased estimates of our true y-intercept and our true slope, even if we have slightly off for our normally distributed residuals. It's also great that larger sample sizes make our model a little bit more reliable, and that this condition is a little bit more robust. So here is a two-step procedure for visualizing this condition. The first step is to use the augment function, which lives in the Broom package. That's B-R-O-O-M. So we're loading in the Broom package using this augment function. And the way that I think of this augment function is it's giving you all of the information about this linear model. So I'm naming a new object called beauty score info, which contains all of the information about this LM. So notably, what we want out of this thing, if we preview it, we see that we get these fitted values, which we'll use later. We get these residual values and all of this other stuff. When we're thinking about visualizing the distribution of residuals, we want this column of things. We want all of the residuals, and we want to be able to plot the distribution of these objects or these numbers. So keep in mind that when we're plotting this, we're going to use this column name, which starts with a period. It's called .resid. So that's what we're going to do next. Is we're going to take this beauty score info that I made, so this original object that I made here, that's the augment of my linear model. I'm going to take this beauty score info, which is my new data set. I'm going to pipe that into ggplot. And the thing that I want to visualize on my x-axis with a histogram is these residuals. Remember that that name starts with a period. So here I'm piping in my data and visualizing the distribution of residuals. I'm using a histogram. I played around a little bit with the bin width, which is what you'll probably want to do. You can go ahead and start with the default value and see how you can fine tune it from there. So then I chose a bin width that I thought looked pretty good, and I'm adding on an x-axis label. So this is using the xlab option. You can also use the labs function and say x equals residuals. So this is the code that we need. So this is our two-step process. First, we have to get the augmented information. So we need to use this augment function to get the information, specifically to get these residuals. The next piece is to use that information, that new augment data set, to use the residuals and plot the distribution of them. So then let's talk about, well, what do we think about this? So when we're looking at assessing distribution for normality, what looks like, well, this isn't completely a normal curve because clearly it's got a little bit of a short right tail, it's got a long left tail, and it's got some sort of like, it's not very continuous going on. We also notice that the center or the mode is actually not at 0, which is definitely not what's going on in a normal curve. But does it look like it's approximately bell-shaped and symmetric? Yes, it looks like it's approximately symmetric. It's a little bit shorter over here than it is over here. It does have one mode, which is something that we want to make sure that we're looking for. And even though that center is like slightly shifted off of 0, it's not that far from 0. It's around 0.5. So I wouldn't say that this is a super big concern for me. So I would say that in total, I would not assume that this condition is violated. I would be very careful with my language. I would not say that the condition is met because I don't feel certain that this looks exactly like a normal curve, but I don't believe that the condition is violated based off of the way that this distribution looks. So that is how we assess normality. The next piece is assessing equal variance or equal variability. So the idea is that the variability of the points around the least squares regression line remains fairly constant as I go across my x values. So that means that I don't have the trend where larger values of x have larger variability in y, which looks something like a funnel, where it's funneling out or it's funneling in. So I want to have this sort of band across my regression line where it's approximately the same width as I go from my lower x values to my larger x values. So the way that we do this is we're still using that same information piece where we have this beauty score info idea where we have all of those values from our linear regression. And here we're using two pieces from that. We're using our residuals here, which we used before, but we're also using our fitted values. So this is what's producing that plot that I showed you before, which is called the residual versus fitted. So our fitted values are on our x, our residuals are on our y. We're visualizing each of those with a point, so we're kind of creating a scatter plot of sorts. This idea is that I'm creating a horizontal line. So let me show you what this looks like. This is a horizontal line at 0 with a dashed look, and it also is colored red. So that's what I have here. I say I want a GMH line, which stands for horizontal line. My y-intercept is 0, which puts it at the origin. I want it to be a dashed line, and I want it to be red. So that's what this is. Here I'm using my labs function because I want to name both my x and my y axes. I'm going to name my x-axis the fitted values and my y-axis the residuals. So that's what this ends up looking like. Each of these points is a plot of the fitted versus the residual value. I have this horizontal line that goes all the way across, showing me exactly where my regression line was, where the residuals are 0. And then I can name my axis labels so I have better labels like residual and fitted values. So then what we can do is we can take this plot and decide what do we think about this assumption. So what we're looking at here is this dashed 0 line. That's effectively our regression line. So any points that fall on this dashed 0 line, those are points that fell really close or on top of the regression line. So here that's where our fitted values, so as we're noticing as we go across our larger fitted values, this is where our regression line lies. So then when we are looking at our residuals, our positive residuals correspond to values that were above the line. Negative residuals are values that were below the line. But essentially what we're looking at is we're looking at as I go along my fitted values, or these x values, does it seem like the spread from top to bottom is about the same as I go across these values? It looks like here at the beginning we have a spread from about negative 1.5 to about 1. And as I go across, it does look like it gets a little bit shorter here, but then it gets about back to the normal. So it seems like across these values, it doesn't seem like the variance is changing that dramatically. So I would not say that this condition is violated. We would not say that the condition is met because mathematically we know that this area right here is a little bit different, which means that our condition is a little bit violated, but we don't think it's bad enough. So what we would say is we don't believe that the condition is violated enough to warrant any sort of concern. So this is how you could assess equal variance and normality using these plots. I hope this helps a little bit, and I'll see you all later.